Google handles over 3.5 billion searches daily, a figure that's constantly growing. Ranking these results requires complex machine learning models analyzing hundreds of features in milliseconds. The secret is a combination of clever algorithms and distributed infrastructure. In this video, we'll explore the architecture behind Google Search, from crawling and indexing to query understanding and ranking. Remember this number, 3.5 billion. We'll see why it matters when we discuss scaling. Here's what most engineers get wrong. They underestimate the complexity of query understanding and feature engineering. Few people know that Google rewrites 25% of queries to better match user intent. This is a hybrid approach, combining keyword matching with semantic understanding. Think of Google Search like a librarian who understands what you're looking for, even if you don't know the exact title. This is where most engineers go wrong. Let's define the scope. Functionally, we need keyword-based search in delivering relevant results at scale. Non-functional requirements include low latency, under 200 millers, high availability, 99.99%, and scalability to handle increasing traffic. Clarifying questions. Should we support personalized results? For this exercise, we'll focus on text-based web search with personalization. We need to support a REST API endpoint, like post, API v1.search, query, user ID, page, results. This API should handle millions of requests per second. A common mistake is not clarifying the non-functional requirements up front, leading to designs that can't scale. We also need to consider the crawler and indexer components, which are responsible for discovering and indexing web pages. The crawler discovers new and updated content on the web, while the indexer builds the inverted index for fast lookups. Now let's estimate the scale. 3.5 billion daily searches translate to roughly 40,000 queries per second, QPS. Each query averages 500 bytes, resulting in 40,000 times 500 equals 20 Mbps of query traffic. Storing 10 billion documents, averaging 10 kbytes each, requires 10 billion times 10 kbyte equals 100 TB of storage for raw documents. The inverted index, which maps terms to documents, will likely be 2-3x this size, so let's budget 300 TB. Bandwidth for serving search results depends on average result size and results per page. We'll need to serve 10 results per page, each across 20 kilobytes, totaling 200 kbyte per request. This means we need 8 GB of bandwidth. These estimations will guide our design choices later on. We'll also need to estimate the storage and processing power required for the ranking models, which can be significant. These calculations are crucial for capacity planning and ensuring our system can handle the load. So at a high level, the system consists of key components. The user's query hits a load balancer, then an API gateway. The API gateway routes the query to services for query understanding, document retrieval using the inverted index, and ranking. Retrieved documents are ranked by a machine learning model and returned. A separate indexing pipeline builds and updates the inverted index. To handle the read-heavy workload, we'll heavily rely on caching. And we use Kafka for asynchronous indexing because it provides ordering guarantees and fault tolerance. SQS was considered, but it lacks Kafka's strong ordering. We also use a CDN to cache static content like images and CSS because it reduces latency and offloads traffic from our servers. The reason we use a CDN is because it's geographically distributed, bringing content closer to the user. Here's the twist. The ranking service is the most complex part, requiring significant computational resources. This is where most engineers make a critical mistake. They underestimate the complexity of feature engineering and ranking model selection. Remember the 3.5 billion searches? This architecture is designed to handle that scale. The API gateway uses rate limiting to prevent abuse and ensure fair usage. Now let's dive deeper into query understanding and ranking. The query understanding service performs spelling correction, stemming, synonym expansion, and query classification. For spelling correction, we can use edit distance algorithms or a pre-trained language model like BERT. BERT uses a transformer network to understand the context of words in a query. Stemming reduces words to their root form. Synonym expansion uses a thesaurus or word embeddings. The document retrieval service uses an inverted index to find documents. The ranking model scores each document based on features. Your interviewer might ask, why not just use a simple BM25 ranking function? BM25 doesn't capture complex relationships between queries and documents. We use a lambda-mart model a gradient boosting algorithm learning nonlinear relationships because it balances performance and training cost. DNNs are an option, but LambdaMart is more efficient to train. LambdaMart uses decision trees to approximate the ranking function, allowing for efficient updates. Stop. Think about this. The choice of ranking model significantly impacts search relevance. A common mistake is not considering the computational cost of different ranking models. For example, if we have a sudden spike in traffic, the ranking service could become a bottleneck, leading to increased latency. To mitigate this, we can use model distillation to create smaller, faster models. Model distillation involves training a smaller model to mimic the behavior of a larger, more complex model. The features used in the ranking model include TF-IDF scores, PageRank, and click-through rate. The secret is feature engineering. We also use relevance metrics like mean average precision, MAP, and normalized discounted cumulative gain, NDCG, to evaluate the ranking model's performance. Let's consider the data model. We'll use PostgreSQL for document metadata and the inverted index because it offers strong consistency and supports complex queries. The document metadata table includes document ID, URL, title, content, and PageRank score. The inverted index table stores term document ID pairs. Indexes on document ID and term columns are crucial for efficient retrieval. The schema includes audit fields like created at and updated at, and data lineage tracking with parent ID. Pause here. What's missing? We also need budget consumed for differential privacy. Without it, we risk over-personalization and privacy violations. We chose PostgreSQL over Cassandra because PostgreSQL supports ACID transactions, ensuring data consistency during updates to the inverted index. Cassandra was considered, but it lacks the ability to easily perform complex joins. PostgreSQL also provides geospatial indexing, which could be useful for location-based search. We also need to store clickstream data for personalization. To handle the high read volume, we'll use caching layers, a CDN for static content, and a Redis cache for frequently accessed documents and query results. For the inverted index, we'll use sharding, distributing data across servers. Consistent hashing ensures each term maps consistently to the same shard. We replicate shards for fault tolerance. Remember the 3.5 billion searches. To handle that, we need to scale caching and sharding. Your interviewer might push back, why not memcached instead of Redis? Redis offers richer data structures and persistence, useful for caching query results and document metadata. Memcached is simpler, but lacks these features. We use consistent hashing because it minimizes data movement when adding or removing servers. A simple hash would cause massive reshuffling. This is where most people go wrong. They don't consider the impact of data movement during scaling. For example, if we add a new server, only a small percentage of the data needs to be moved, minimizing disruption to the system. We can also use Bloom filters to reduce the number of unnecessary lookups in the inverted index. We can also use query expansion to improve recall. Now that we've scaled the system, reliability is crucial. We'll use replication for all critical components. If a server fails, we automatically failover to a replica. We'll also implement monitoring and alerting to detect and respond to issues quickly. We'll use a health check endpoint for each service to ensure it's running correctly. We'll monitor key metrics like QPS, latency, and error rate. An experienced interviewer will probe what happens during a network partition. We'll use Raft consensus for leader election to ensure consistency even with network issues. Raft ensures that only one leader is elected, preventing split-brain scenarios. This ensures that even if some servers are isolated, the system can continue to operate correctly. This is especially important for the indexing pipeline, where data consistency is paramount. In summary, we designed a scalable and reliable search engine using caching, sharding, and replication. The key trade-offs were between consistency and latency. We chose eventual consistency for most data to achieve low latency. Potential bottlenecks include the ranking model and the inverted index. Next steps include implementing personalization, A/B testing, and online learning to continuously improve search results. Remember the 3.5 billion searches? This architecture allows us to handle that scale efficiently and reliably. We also need to consider the crawler and the indexer components to keep the index up to date. The crawler uses a politeness policy to avoid overloading websites. We can also use query expansion to continuously improve the ranking model,